Hello, my name is Sean, and these are my group members William and Ton. Today, we will go over the game Cross Country, which is a custom game we programmed in Python, and how we incorporated a self-learning agent in it. Specifically, we used the Q-learning algorithm and deep Q-learning algorithm and compared the results in the end. In the game, there is an agent whose goal is to reach a reward tile somewhere on the map. However, there are obstacles in the way that penalize the agent, and so the agent must learn how to reach the goal tile while suffering as little penalties as possible. Specifically, the grass tiles penalize the agent by 1 point, the mud tiles penalize the agent by 2 points, and the water tiles penalize the agent by 10 points. The reward tile rewards the agent with 100 points, and so the agent should learn how to reach it optimally while also learning the penalties of the other tiles.
Starting with Q-learning, we initialize the map and terrain reward and penalty values, available actions, and goal state. The reward table defines positive and negative values for the cells within the game world and also represents the agent's knowledge. Training goes for 3,000 epochs or 3,000 runs. Each epoch ends when the agent reaches the goal tile, exceeds move limit, or the penalties get over a certain amount. As the agents keep doing runs, the Q table continues to update based on the learning rate, which controls the intensity of the changes to the Q table values, along with the discount value for reward prioritization. The rewards themselves after each action and max Q value. The history results are saved to a JSON file with each epoch run, which then allows us to run another program to visualize or render each epoch individually to see how they progress. As you can see, it only takes about half the amount of allocated epochs before convergence with our current values.
Now we implement the deep Q-learning algorithm for our game. A key difference between deep Q-learning and Q-learning is on how the Q values are represented and computed. In Q-learning, a Q table is used to map a state action pair to corresponding Q value. However, in deep Q-learning, the Q table is displayed with a neural network. Instead of storing a Q value for all state action pair, the neural network takes the input state and predict the set of action Q value pair. This approach makes deep Q-learning scalable to problems with large state space. One important aspect to note is that training time for deep Q-learning is significantly longer than deep Q-learning. This is because the neural network training involves iterative optimization, backpropagation. In our case, the number of epochs required to achieve a scalable, stable performance were approximately 2,500. To summarize, Q-learning and deep Q-learning both achieve similar performance in our game with a maximum score of 82 points. However, they differ in complexity and scalability. Q-learning is simple, fast, and consistent, but it is limited to small environments due to its reliance on the Q table, which grows exponentially with the Q state space. Deep Q-learning is slower and more complex due to the neural network, but it is better suited for handling large environments and continuous space. Its performance can vary due to random initialization of weights, but it offers a robust approach for more complex problems.